morning everyone. I am Tanushree from Civil Engineering branch. So you know that in the last class we have completed the derivation part of the torsion up to this much. So today we will continue from here where we have already calculated the value of shear stress for the small elementary section, the value of turning force, and also the value of twisting moment for the small elementary ring section. And now, by integrating the equation of twisting moment of the small elementary ring section with the limitation of 0 to capital R, we can find out the total value of torque for the whole circular shaft. So now T is equal to tau by R, which is the common, so that we separate this from the integration part, and then integration of 0 to capital R, and here we have already put R square value into dA. That R is the small r value, that is the value of radius from the center to the small elementary section. Hence, this value, that is the integration of R square into dA, is the value of polar moment of inertia. Okay. So let us recall here the basic concept of polar moment of inertia. We can write here the formula for polar moment of inertia. Further, we will use this formula of polar moment of inertia in the above equation. Hence, we can put in this place the value of J. J is the symbolical representation of polar moment of inertia. Hence, the total equation is converted into T is equal to tau by R multiplied by J, that is polar moment of inertia. Hence, by putting this J value here, we can find out half of the torsion equation, that is T by J is equal to tau by R. So this is all about your torsion equation. Then half of the torsion equation we have to derive now. So in this part we have to consider the angular deformation for the twisting moment in the shaft section. So as you can see, this is the part of fixed support for the shaft, and this is the neutral axis along the length of the shaft. And then due to the twisting moment, that is the torque, this value, that is the axis of the longitudinal direction, is deformed to here. That means this D value is deflected by D dash. So here at the center of the angle section, that means in this point, we got some deformation or angular displacement, which is denoted as theta. Okay. And now we have to consider the circular section of the shaft. So you can see this is the cross section of the shaft. Okay. And capital R, that is the radius of the circular shaft, and T is the twisting moment or torque, and this angle is the angular displacement due to the torque T. So now let the shaft is subjected to a torque or twisting moment T, that you can see in this figure, and hence every cross section of this shaft will be subjected to shear stress. Now we have to find out the shear strain value, as we know that in case of shaft section, due to the torque in that shaft, shear stress is developed. So hence shear strain also occurs. So we can say now change in arc in outer surface is d dash, that is this point to this point, and in the cross section that is here to here. So this is the displacement, or you can say the deformation due to the torque. So the deformation or the change of dimension is d dash, and the shear strain at outer arc is dd dash divided by cd. That is, we know that strain is equal to change in dimension divided by original dimension. So before the torque is applied, the original size or original dimension of the shaft is C to D. So this is the original dimension of the shaft. But after the provision of the torque, it is deflected from this point to this point. So we can say the change of the dimension is d to d dash. Hence, the change in dimension is d dash and the original dimension is cd. So we can put the shear strain value as d dash divided by cd. And cd, you can see the cd value is equal to the total length of the shaft, that is from here to here. So CD value is the total length of the shaft. So we can put the capital L value in the place of CD. Hence d dash divided by capital L is the shear strain value for the shaft. So now, according to the geometry, we know that the arc value, that means this much value, we can find out by multiplying two things. One is the radius and another is the angle. So here the radius value is capital R and the angle it is produced as theta. So we can say the d dash value is equal to R into theta. So here in the place of d dash we can put R theta value. Hence the total value of shear strain we can convert it into R theta divided by capital L. And now the modulus of rigidity, which is symbolized as capital G or capital C. So we know that modulus of rigidity is equal to shear stress divided by shear strain. That is, the ratio between shear stress to shear strain is equal to the modulus of rigidity. Hence, the shear stress of the shaft is equal to tau, as we know in before, and shear strain value we calculated as R theta divided by L. So hence we can put this value here, as we got the value of modulus of rigidity by solving on this thing as tau L divided by capital R into theta. From here we can put the value of G is equal to tau L divided by R theta, and by simplifying it we can find out the equation of torsion as G theta divided by L is equal to tau by R, and previously we got the value of tau by R is equal to T by J. Hence we can say that tau by r is equal to T by J is equal to G theta by L. So this is your total equation of torsion. So hence we got the value of equation of torque, that is T by J is equal to tau by r is equal to G theta by L or C theta by L, where C or G is equal to modulus of rigidity, L is your length of the shaft, and theta is your angle of twist in radian. So now the polar moment of inertia have some formula according to the circular section. So here is your formulas. So first of all, if the circular section is total solid, so when the circular section is fully solid section, then you can find out the polar moment of inertia as pi r square by 2 value. So here, if the radius value is given, then you can put this formula. After that, if the circular section is hollow type and the thickness of the hollow circular section is more, then here you can put this formula, that is pi into r0 to the power 4th minus ri to the power 4th divided by 2. So here r0 is the radius from the center to the outer circular section and ri is the radius of the inner circular section. Then third one is your again hollow circular section, but here the thickness between two circles is small. So here you can put the value as 2 pi t into r average to the power q, where the r average value you can find out by r0 plus ri divided by 2. So r0 is your radius of the outer circular section and ri is the radius of the inner circular section. And after that, another term is there, which is power generated through the shaft, and power generated through the shaft is denoted as capital P. So as we know that P is equal to force into distance, but in case of torsion, the force is your average torque and distance is your angular displacement. So hence, here the total formula is T into 2 pi n divided by 60, where T is the torque value and n is the revolution of the shaft due to the torque. And by this formula, we can find out the power generated through the shaft. So now we can solve some formula or some numerical regarding the torsion. So this is your first question regarding torsion. So here a shaft of 50 mm diameter and 0.7 meter long is subjected to a torque of 1200 Newton meter. Calculate the shear stress and the angle of twist, where G is equal to 90 GPa. So first of all, we have to write down what are the data given of the question. So first of all, the diameter of the shaft is given, that is 50 mm. So now we can convert this mm value into meter. So we have 0.05 meter of the diameter. Then the length value is given, that is the length of the shaft is given, which is 0.7 meter. And after that, the torque of 1200 Newton mm is given. So T value is given, which is 1200 Newton mm. And last,